That's the direction of travel, and as the electric field oscillates like this, the magnetic field will oscillate like that. That's a plane wave, okay? And that's not how the wave looks like when it comes from a light bulb. It's going in all directions, but we'll keep it simple. That's why this is called an electromagnetic wave. It has both electric and magnetic fields. The electric and magnetic fields are perpendicular to each other, and they're perpendicular to the direction of travel, okay? So this electric field is oscillating like that. And you see when the electric field is there, the magnetic field is there, and that's the direction of propagation. For this light, the frequency is, okay, so the electric field, this is one oscillation. For visible light, electromagnetic waves oscillate, the frequencies are on 10 to the power of 15 hertz. Okay. So it's oscillating about 1,000 trillion times a second. Yeah. And so, by the way, the energy of a photon is h, the Planck's constant, times the frequency. So higher the frequency, higher the energy content of that photon. Okay. So UV light has more energy than visible light, and so on. Okay. X-rays are more energy than UV light, and so on. Gamma rays are some of the most energetic light. Okay. All right. So like I said, around 1880, Mr. Maxwell discovered that there must exist electromagnetic waves, and he realized light was an electromagnetic wave. Okay? So until then, we didn't know what light, the nature of light was. Until then, we didn't know that the nature of this beam was that. Okay, light was like that. All right, so now let's, I'll go through the equations. Okay, so these are Maxwell's equations. What this equation tells you is, and we've studied this in a couple of chapters ago, time-varying magnetic fields produce electric fields, and this equation tells you time-varying electric fields produce magnetic fields. These equations are integral forms of this equation, so they contain the same information. So this is a differential form, this is an integral form. Okay, so this is Faraday's law. Time rate of change of magnetic flux is equal to the line integral of that, which is the EMF. Anyway, here's how it looks in pictures. Okay, so what this is showing you is, if you have a magnetic field that's increasing in this direction, it creates an electric field like that all around it. Okay, how would you increase a magnetic field in this direction? How could you do that in practice? Okay, so you could have a wire like this, and pass a current in like that. And as you increase the current, the magnetic field here would increase, and it would induce an electric field in this direction, which would produce a current in the opposite direction. But anyway, if you somehow increase the magnetic field in this direction, it produces an electric field. That's what this equation is telling you. Time varying magnetic field, magnetic flux is equal to the EMF produced. This is that equation. This equation tells you time varying electric field. So if you have an electric field like this that's increasing, it produces a magnetic field in that direction. Okay. So that's what these two equations tell you. Okay, so time varying magnetic fields produce electric fields, and time varying electric fields produce magnetic fields. And so this is at the root of the propagating electromagnetic waves. As this electric field oscillates, it's producing a magnetic field, and as the magnetic field oscillates, it's producing electric fields. Okay. All right, so here are the Maxwell's equations again. Okay, so what Mr. Maxwell was doing was, one afternoon he started playing with these equations, and he wanted to see what kind of solutions they would have in vacuum. Okay, So in vacuum, there are no charges, so this would be 0. So in vacuum, if there is any electric field, divergence of the electric field has to be 0. Divergence of B has to be 0. Curl of E equal to minus del B by del T. Curl of B, this is a current density, so that would be 0 in vacuum. Okay. So here are the 4 equations. This is one afternoon after his lunch. He's going to look for solutions for these guys. Okay. Here is a vector identity, vector field identity. You can take any vector field and do this curl of this vector is equal to gradient of divergence of the vector minus del square by del square A of the vector. Okay. So this is true for, this is an identity, it's true for any vector field. So let's apply it for the electric field. Okay. Well, Maxwell's equation already tells you that the electric field has to satisfy this equation. So now what we'll do is we'll take the curl of both sides. Okay, so this is a vector field. From the identity, this should equal that. Gradient of divergence of E minus del square E. And if when you study partial derivatives, you'll see that if, let's say you're taking a partial, you have a function f x y, you can take the partial derivative with respect to x first and then with y, or you could do y first and x next. Okay, so you can interchange the order of derivatives. Okay, you guys are doing this right now in calculus? Are you guys doing this in calculus?
I'm not a checklist right
I already passed calc 3.
All right. Anyway, so what that means is you can take the curl and the time derivative are interchangeable. So minus del by del t, curl of B. But curl of B, see, curl of B is that. So we're going to substitute that. So now I'm going to, and by the way, so the divergence of E in vacuum is 0. This guy drops out. So you have minus del square E equal to minus del by del T. And curl of B was epsilon naught mu naught del E by del T. Okay, all we have done is substituted this. All right, so what you get is, so I'm writing all over, but del square E equal to minus epsilon naught mu naught del square E by del T squared. And that's that. That is the wave equation. So the electric field in vacuum satisfies the wave equations. Okay? And if you take the solutions of that, well, just like you saw on the string, you get traveling wave solutions. You'll similarly find an equation for the magnetic field. Okay. And okay, so now this in general it's hard to solve. So this equation has solutions to light traveling from the sun equally in all directions. But we'll look at plane wave solutions. Those are the simplest solutions. And that's the picture that I showed you. That's the picture. That's this picture. Okay, so let's do that. And also the fact that E and B are related like this, what this equation will tell you is if E is in the x direction, is E points in the x direction, this will point in the, so, no, if E is in the y direction, B will point in the z direction. Okay, so that's what this equation tells you. Again, okay, we won't worry about all of that, but if E is in the y direction, this will be in the z direction. Okay, all right, so here's the wave equation. Okay, so we'll consider the simplest case solutions. All right, so we have del square E equal to um, right, and it turns out that so when was Mr. Maxwell doing this? 1880. When had we measured the speed of light? 1800.
Oh.
Okay, so we had measured the speed of light then. Okay, and this, funnily enough, this constant mu naught epsilon naught was equal to 1 over c squared. That's when you realized electromagnetic waves were, light waves are electromagnetic waves. All right, del square, this operator, I haven't mentioned this yet, but this del square operator is the following: del x square and so E is that. E is a function of x, y, z, and t, and this is equal to 1 over c squared. So that's a wave equation, and we're looking for solutions for this. Okay, so what we'll do is we'll look for the simplest solution. Okay, so we'll look for solutions something like this. We'll look for a plane wave solution. So it's in the y direction, and E changes only with x. See, E is changing with x as you move in the x direction, and it's E is changing with t. So the simplest solution, we'll look for a simple solution, and E, x, y, z, t. Let's look for this. E in the y direction, J. And this will imply that B is in the, B is x, t, k direction. Okay, so this is the kind of solution we'll look for. So E is only a function of x and t. So this guy drops out, this guy drops out. You have only this guy and that guy. Okay, and we won't even put the vector, so we'll just put that. So del square, del x square, E x t equal to 1 over c squared. And similarly, you'll get an equation for the magnetic field, del square by del x square. Okay, where x, I've just written the magnitude, but the electric field vector, it really has only the y component. And the magnetic field has a z component. So that's the solution we're looking for. right? And these are easy to solve. You don't have to have Maxwell for this. Even I can solve this. Okay. And here's the solutions. Okay, so to that differential equation. So that's a wave equation. Okay, so Mr. Maxwell, looking for solutions in vacuum, found that there exist electric and magnetic fields that satisfy the wave equation. So you have traveling wave solutions. And they travel at the speed of light. So light is an electromagnetic wave. Okay. So here are the two wave equations. Again, the wave equation relates second order spatial derivatives to of the field to second order time derivatives. Yeah. All right, so here is the solution. This is how it looks. There's the direction of travel. The electric field is oscillating like that. The magnetic field is oscillating like this in a perpendicular direction. Okay. And here are the solutions. E is equal to, there's the amplitude of the electric field, the amplitude of the electric field. Cosine kx minus omega t, k is the wave vector, omega is the angular frequency. Which direction is this wave traveling? Do you guys remember? To the right. Okay. As t increases, x has to increase to keep the phase constant. Okay. And b is, so there's the amplitude, k. Okay. K is related to the wavelength, 2 pi by lambda, and omega is the angular frequency, 2 pi times f. So for this wave, there's the wavelength. Okay. And for visible light, wavelength is related to the color you see. Okay. So for instance, this green laser has a wavelength of around 550 nanometers. Okay. Red wavelengths have around 650 nanometers. Yeah. So we'll use a red laser in lab next week. Okay. All right, so that's the wavelength. Okay, so here's a traveling wave traveling to the right. And the speed of light, speed of the wave is given by frequency times wavelength, omega divided by k. All right, so again, we did a lot of technical stuff, but let me summarize this again. What Mr. Maxwell did in around 1880, here are the Maxwell's equations that described all electromagnetic phenomenon. And he's studying these equations in vacuum. In vacuum, this term is 0, this term is 0. So there's this equation. So what these equations tell you is, no matter what kind of electric and magnetic fields you have in vacuum, they must satisfy these equations. You can't have an electric and magnetic field that doesn't satisfy this equation. Okay? And so these equations tell you that there must exist traveling electromagnetic waves. Very powerful. Okay. All right, so now let's, and these waves travel at the speed of light. Okay, so what all kinds of waves are there? Let's see. So let me show you the electromagnetic spectrum. So all these types of different waves are all electromagnetic waves. So radio waves. So you have sensors for electromagnetic waves. Where do you have your sensors? Where? Yeah. So on your retina you have cells that can detect these wavelengths. Yeah. So a very narrow band. Okay, so that's the visible light, and these. So this is longer wavelength, shorter wavelength. This is higher frequency. So the frequency is increasing in this direction, and so these are all longer wavelength. Okay, so your sensors work for these wavelengths from 700 to 400 nanometers, and different wavelengths appear different shades to you. Okay. And by the way, so what this is showing you is if you want to see an object this size, you have to use a wavelength of light that is that size or smaller. So if you want to see this guy, you can't use this wavelength of light. You can't use any longer wavelength. Okay, so here's a fundamental point. If you want to see something, this object, you have to use a wavelength of light that is this wavelength or shorter. Okay. So for instance, you can use, so to see molecules, you need X-rays. Using X-rays, you can see all these guys. We call him Superman because we can only see this stuff, and he can see this, all this stuff, so he can see a little more than us. Okay, so these are all electromagnetic waves. Okay. All right, so now let's, so here are some properties of these electromagnetic waves. Okay. So going back to this, okay, so all waves carry energy, okay, and so if you have electromagnetic waves, they must carry energy too. So once Mr. Maxwell predicted them, Mr. Hertz went looking for them, and here was his setup. Yeah. So Mr. Maxwell predicted traveling electromagnetic waves, and here Mr. Hertz went looking for them, and here is his setup. Okay, so here is this is a capacitor, this is an inductor. You guys remember this is an oscillating circuit, and its frequency at which it oscillates, omega, is equal to 1 over LC, square root of LC. So here's a AC source that's pumping energy into it, and this guy emits electromagnetic waves. And if electromagnetic waves carry energy, Mr. Hertz argued that he should be able to pick up this energy, and he used another tuning LC circuit to pick up whose frequency matched that frequency, and he picked up energy there. Okay, so here was energy transmission via electromagnetic waves. But we all knew this. You go stand in the sun and you feel warm. But this was producing and receiving electromagnetic waves. Okay, so this was the first wireless transmission. Yeah. That we understood. Okay. All right. You can stand anywhere in an electromagnetic wave. You measure the electric field at that point, measure the magnetic field at that point, and the ratio of the electric field to magnetic field is equal to the speed of light. Okay, anywhere. So the amplitude also satisfy that equation. At every instant, the ratio of E and B fields in an electromagnetic wave is equal to the speed of light. Both E and B satisfy the wave equation. You saw that. So here's the simplified wave equation. And the magnetic field also satisfies that equation. So in vacuum, they travel at 3 times 10 to the 8 meters per second. In water, the speed is 2 times 10 to the 8 meters per second. In all other medium, in vacuum, electromagnetic waves travel the fastest. In all other medium, they travel slower. Okay, and the slower they travel, the higher the refractive index of the medium. E and B fields in a plane wave are perpendicular to each other and to the direction of travel. So there's the direction of travel, there's E field, there's magnetic field. Okay? This relationship is true only in vacuum. electromagnetic waves obey the principle of superposition. So what that means is, if you have multiple beams reaching a spot, if the electric field of this guy is that and the electric field of this guy is in this direction, the net electric field is just the sum of these two vectors. Okay, that's the principle of superposition. So these are numbers for a radio wave. So this is a 40 megahertz wave. Okay. What are your FM radios? What are the frequency of FM radios? $90 megahertz, about 100 megahertz, okay? So it's twice this frequency, and speed is frequency times wavelength, okay? All right, so about 50 megahertz, the wavelength is about 8 meters. 8 meters is roughly half the width of this room. So for FM radio, the wavelength is about a quarter of that. So about roughly, FM radio has a wavelength of 2 table width. Okay. So amplitude of the electric field, of course, it depends on the intensity. So energy carried by electromagnetic waves. All waves carry energy. Okay. So now the question is the following. Let's say you have a beam like that. So this was a laser beam, was a very thin beam, but imagine a very large beam of light. The question will be, how much energy is flowing past a point per unit area per time? And this is called the intensity of the beam. So more energy flows, higher the intensity. More energy is being carried. And this intensity is given by the Poynting vector. So power, energy per time, per unit area is the intensity of the beam. Okay. And this intensity of the beam is called the Poynting vector, after Mr. Poynting, who discovered this, okay, who came up with this formula. It's 1 over mu naught E cross B. So for instance, the average value of this, the intensity of sunlight at Earth, so if you go 100 above the atmosphere, the sunlight, the intensity is 1400 watts per meter square. Watts is 1400 joules per second. So what this means is, so if you go about this, so here the sun, here the earth, here the atmosphere. At every meter square, the amount of light falling is 1400 joules per second. That is 1400 watts. 14 times 100 watts. So it's like 1400 watts are shining on every meter square. Okay, this number is important. If you could harness only 1 part in 10,000 of this, only 1 part in 10,000 of this sunlight, you can serve all of mankind's energy needs. Okay. So, Mr. Elon is talking about putting solar farms up there now that he can launch stuff for cheap. And the Japanese have been talking about this.
How do you ship the energy down?
Microwaves. Mm. Yeah. Well, this is all solutions that you aerospace engineers will have to come up with, okay? Or whatever the engineer. All right. All right, so intensity of the beam is given by Poynting vector. Okay, you guys saw that E and B vary sinusoidally. Okay, so the energy is really coming in spurts. Okay, but what is the frequency of that spurt? For visible light, that's 10 to the power of 15 hertz per second. It's like 10 to the power of 15 pellets per second, except that you can't see that. So most of the time, all we are interested in is the average value of the Poynting vector. And the average value of the Poynting vector works out to be that. E max, B max over 2 mu naught. So that's the intensity. You know? And okay, so if you have a beam like this, okay, so the amount of the length of beam that passes you by in 1 second is equal to the speed of light. That's the length that will pass you, okay? 300,000 kilometers. That beam will pass you by in 1 second. Okay, and so what we say is the amount of energy that passes you is this, the energy contained in 1 meter cube volume times C. That's what this is. The intensity is the energy contained in 1 unit volume times C. Okay, and so the energy content of the electromagnetic wave can be given in terms of just the electric field or the magnetic field. That's what that is. So if you have a beam of light, you take a little volume of that light and you want to know how much energy there is per meter cube. That's what this is. Okay. So, and you can also see from this guy, from this formula, the more intense a beam, remember E and B are related. What does more intense beam means? It means the amplitude of the electric field is higher. Okay, so remember B is related to E over B is equal to C, so B is E over C. So this is equal to E max squared over 2 mu naught C. So if you double the amplitude of the electric field, the intensity of the beam is 4 times as great. Yeah. All right, let's say you fire a bullet. It has kinetic energy 1/2 mv squared. What else does the bullet have? Does it have momentum? What is the momentum?
Mass times velocity.
M times V. Okay, so you see the momentum is energy divided by velocity, aside from the factor of 1/2. Okay, so when you have a beam of light, you can think of a beam of light now. We realize all of this. The beam of light as a stream of photons. Okay, so this must carry. It's like firing bullets, and this must carry momentum. Okay, so the momentum carried by a beam of light is the energy. So think of a beam this big. It has energy U. What is the momentum of this beam? U divided by C. Okay. Energy divided by speed gives you the momentum. Okay, so if I hit you with a beam of light, okay, so let's say I shoot this for a little bit, half a second, so there's this beam that's 150,000 kilometers. And if you absorb that, that's how much momentum is transferred to you. Okay. You can go to UCF and they can shoot a beam at you that is an attosecond long. So let's figure this out. An attosecond is 10 to the minus 18 seconds. Okay. So the distance this would travel is CT equal to 3 times 10 to the 8 meters per second. 10 second. Okay, the size of an atom is 10 to the minus 10 meters, roughly. So this is roughly 3 atoms big. So they can shoot a beam at you, which is about 3 atoms big. Okay. Yeah, so they can turn it on and off at
Do you
that.
see a flash?
What?
Do you see the flash?
No.
What does that do to a person? sitting
What?
on the phone?
So there you go. That's a good question. So why would you need this? Okay. So let's say we get a reaction going, oxygen, and we'll keep it simple, hydrogen. You shoot a bunch of oxygen and hydrogen together, and they are combining, and you shoot them with this beam of light. So from the scattered light, you can see different stages of a reaction. Something that's going on that fast, you can see with that. That's the kind of stuff it's useful for. So if you want to study a phenomenon that's happening over that time scale, that's what you want. Again, that's what strobe lights do. You guys have seen strobe lights. If something is moving at a certain speed, you want to see it evolving slowly. You want a strobe that's coming on and off at that speed. You might have seen that in your, when they want to see how, when the fins of a jet engine are rotating, or you can use strobe lights too. So that's what, okay. All right, so a beam of light carries momentum, and the amount of momentum is U over C. So if you absorb that beam, that's how much momentum hits you. The greater the momentum that hits you, if a large bullet hits you, you go flying. So we could shoot you with a laser gun and make you go flying, except it has to be very intense laser. The momentum transferred to you, if the light reflects off of you, is twice as much. Yeah. So when you take a bullet, if the bullet bounced off of you, you would fly twice the speed. Yeah. So, Superman, you shoot Superman with a bullet, he flies twice the speed. You shoot me, only, but then the bullet embeds in me and I'm dead. All right. Pressure, light can exert pressure. Okay. Pressure is force over area. Force is rate of change of momentum transfer. Okay, so 1 over area. So here's the area. Momentum is P U over C, and D, so pressure is force over area. And if you're absorbing the beam, the momentum you absorbed is this, dt, and 1 over C U over area d by dt of that. And this fella is intensity. Intensity is measured by the Poynting vector. So the pressure exerted by a beam of light, if you absorb the beam, is S over C. Okay. And of course, if the beam is reflected, the pressure, that is the force per unit area, is 2S by C. So if you want to calculate the pressure of the of sunlight on this roof, it's roughly the weight of one of your hairs. That's the force that's exerted by sunlight on this roof. Now, is this for real? Or this is just formulas that we are giving you? See, this is for real. Okay, this is a comet, and when it comes close to the sun, you have particles evaporate. Comets are essentially a bunch of water and dirt. Okay. And then some of the gas ionizes as well. And from the sun, you get photons emitted. And that's mostly what it is. And protons and electrons emitted as well. Okay. So these photons, light particles, exert a pressure on the dust particle, that is neutral particles, and that's the tail they get. And this solar wind, the ionized particle, pushes on the ionized plasma. So a comet will have two tails. This is the gas tail, and this is the dust tail. This is the tail that is pushed by photons. This is the tail that's pushed by solar wind. Here, this is sunlight pushing a solar sail. We've launched this. Japan launched it a while ago. So humanity has launched it. Yeah. Do you guys, so here's some numbers. Do you guys know how long it takes to get to the moon via rockets?
5 days.
How long did Artemis take? Around 3 days, okay. So if you go to the parking lot, get a car, that much metal, 1,000 kg of metal, okay, so this much metal, pound it into a thin solar sail, about the size of this campus. Dunn Road, White Road, ISB. And put it out there. That'll get to the moon in 11 days from the push of sunlight. So this is real.
How do you slow down?
Well, so,
I guess it's
well, so you can fold yourself, and then the
Solar
push.
anchor,
Hmm?
We're making a whole boat, so have
Yeah.
a solar anchor. You have a solar-
So this is real, okay? So these are all electromagnetic waves, okay? So AM radio, FM radio, microwaves, radars, light, X-rays, gamma rays, hard X-rays, and so on. Okay? And again, the energy of a photon is equal to H times F. The higher the frequency, higher the energy. C is F times lambda, so greater frequency, lower the wavelength.
What was the H again?
Planck's constant. Okay. Hot on an object, so this tells you if an object is that hot, if the surface temperature of a star is 10 million Kelvin, what is the surface temperature of the sun? 6,000 Kelvin, okay? So if the sun is 6,000 Kelvin, that is the peak of the radiation. For a star whose surface temperature is that, it'll be emitting in X-rays. Okay? The sensors that you are born with, the light sensors you're born with, see in this band. Okay? You're most sensitive to this color, roughly 550 nanometers, and that's why tennis balls are colored that. Okay? So you're most sensitive to that, 550 nanometers. Okay? Your sensitivity goes down for higher wavelengths and lower wavelengths. So you can distinguish about 7 million shades. Okay? So every wavelength appears as a different shade. Okay? And that thing can render about 16 million shades. So on the average, you can render 7 million, but there's always outliers, and so that thing covers outliers as well. But electronics is cheap, so. So you saw that, oops. So you saw that electromagnetic waves have electric fields. At any given spot, the electric field is oscillating. For visible light, how many times does it oscillate?
10 to the 15.
Yeah, so 10 to the 15 times a second. Okay. For microwave, it oscillates about 5 billion times a second. So the microwave in your microwave, it's oscillating about 5 billion times a second. Well, why do we talk about this? Okay, so what is a water molecule? A water molecule has a dipole. The oxygen atom is greedy for electrons, so the center of the negative charge is there and the center of the positive charge is there. Okay, so let's do the following. Here's the electric field. Now I'm drawing it in a different way, and we'll put a water molecule, which is a dipole. I'm just going to draw this. What does this electric field do? It exerts a force on the positive charge in this direction and on a negative charge in this direction. So the electric field, here's the dipole, here's a water molecule. The electric field is exerting a force on the positive charge in this direction, negative charge in this direction. It's turning it like that. And now, as it's turning, now you flip the electric field. Now the force goes that way. So the electric field essentially can grab hold of the water molecule. An electromagnetic wave can grab hold of the water molecule. So in a microwave, what you're doing is you're grabbing hold of the water molecule in your food, jiggling it 5 billion times a second. So using electromagnetic waves, you were able to pump energy into every water molecule. And then this water molecule shared its energy with all the. So even your driest food, even your food that you pack, backpacking food, even that food has 70% water. Yeah. So that's how microwaves work. Yeah, so the torque reverses direction 5 billion times a second. Okay. Interactions between the molecules distribute the energy being pumped into them. Okay. So here's how radio waves are produced, by the way. So if you want to produce radio waves, what you do is you grab hold of a charge and make it accelerate. And charge that is accelerating will emit electromagnetic waves. And so the best way to accelerate them is using this oscillator circuit. You pumping energy into this, and this thing is, there's a dipole antenna which is acting like a capacitor. Here's the inductor, and this thing oscillates. Its frequency, oscillation frequency is that. And this dipole antenna is essentially grabbing a charge and making it oscillate like that, and it's emitting electromagnetic waves. So 89.9 megahertz, that radio station, what is it, NPR? Okay, so the oscillation frequency of that guy is that, okay, and it's emitting this wave. And then if you want to catch this wave, what do? You have the same setup in your tuning circuit. So your tuner, its frequency is matching exactly the frequency of the transmitter. Okay? And resonance will excite a large current in your tuner. A dipole antenna is made of two rods connected to an oscillating source. The length of each rod is equal to 1/4 of the wavelength to be emitted. Okay, so you saw that for FM radio, the wavelength is about 2 table lengths, and to emit electromagnetic most efficiently, this has to be 1/4 the wavelength. So this rod is half the size of this table for FM radio. Okay, so that's roughly a little less than a meter. Okay. The intensity of the radiation is highest in this direction, if the dipole antenna is like that. So if you have a radio station, you can't hover over the radio station, you're not going to get any signal. Yeah, so intensity is highest in that direction. What are AM and FM radio? What does AM mean?
Amplitude modulation.
So, amplitude modulation, and this is frequency modulation. Okay, so what this is information has generally low frequency, and what you do is you have this information ride on a carrier wave which is a high frequency. So that's how all radio stations work. Okay, so if you talk, let's say, your speech gets converted to an electrical signal whose frequency is quite low, and that rides on a carrier frequency. And there's two different ways of making this ride on this carrier frequency. Yeah. Okay, so let's show you. And that's the two technologies. So here's information, okay, and there's the carrier frequency. You can see that its frequency is much higher than that. And in amplitude modulation, all you do is you add this amplitude to that, so the carrier frequency, you see the carrier frequency, its amplitude is changing. Yeah. So that's AM radio. The advantage of AM radio is it can the advantage of AM radio is it can bounce off the ionosphere, and you can transmit from here and talk to your friend in Australia. The problem is there's lots of noise interference. So if you don't want interference, you can do frequency modulation. Okay, so you see, again, here's the information, and what you do is you break it up into, you Fourier transform that. Again, simplifying it. You're breaking that into different frequency components, and then you're changing the frequency of the carrier wave. So the amplitude of the carrier wave is constant, its frequency is changing. So that information is packed into the frequency changes. The advantage of this is you don't have any noise, so FM radio is, you don't have any noise. But the only problem is FM radio only travels straight lines. Okay, so you can't have you can't listen to Orlando in New York City. All right.